Okay, now we are back to do the actual thing. I'm interested to play a game, and in that game, I'm curious to know how the function which is given, which is expressed in algebraic format, it looks like. You're just going to put the mirror on that to see how it looks like. The mirror that we are just going to use to see how the function looks like is just a Cartesian frame. We are just going to see that if we put the Cartesian frame in front of this function, how it looks like. That's a fun way to see. That's a fun way to explain what is a plotting of the function. The first step which we are going to do, I'm going to say we have 5 steps to take. The first step is that we have to find the intercepts of the function. We'll look at the function first, and we are going to be first curious to answer one question. If I plot this function, in which points it's going to intersect with the horizontal axis, which is the x-axis, and that's what we call that the x-intercepts. Now, in order to find the x-intercepts, remember, the function, if the function is this, is the Cartesian frame is this, which I'm just going to show that. This is the y-axis, this is the x-axis. I have, let's say, a completely random function plotted on there. You see that this function, it plots. If I call this function f of x, you're going to see that this function crosses the x-axis just at this point, and I'm going to call that x0. What is interesting about that x0 is that when you put your eyes along this direction, this is my eyes, this is my eyebrows, this is my eyeball. When I look at the function, the x-axis from this direction, and when I focus at the point x0, which I'm calling that x-intercept, I see the value which I read for the y mapping is going to be 0. And that gives me a clue that in order to find the x-intercepts, I have to find y equal to 0. Then if I put y equal to 0, in order to find the x-intercepts, then as a result I get 0 should equal square root of the x over x squared minus 1. Now, the key thing now, in order to ask for the x-intercepts, is to find the value of the x that is going to validate the expression which I have written there. First of all, I'm going to remind myself on very key things which I remember from the past. I remember from prior studies that if I have a rational expression which is going to be a over b, if a over b becomes 0, I remember I have one key fact. Necessarily in that case, a has to necessarily be 0 in order that the rational expression which I have, a over b, becomes 0. I'm just going to use that identity into solving this expression. Now, I'm just going to erase these coordinates. Then if I do that, I remember here, this square root of the x, it's like the a which I had, then it has to become 0 in order to solve it for the x, that y becomes 0. Then I say that y square root of the x has to become 0. Now in that case, I'm going to ask myself, in order to do that, how to solve this? In order to solve this, again, I can use one other identity. The other identity which I remember is that if a is equal to b, I can just take both sides raised to the power 2 in order to still preserve the equality between them. I'm going to do the same thing with this. I'm going to take both sides raised to the power 2. Then what do I have here is that I have square root of x, which is going to be raised to the power 2, equals to 0 to the power 2. And you see that in that case, we have another identity, if you are just going to remember, is that if this is this one here, 2 is over there, 2 can go inside, I should say, because like what? Becomes like square root of the x multiplies square root of the x, then it becomes what? Then in that case, you can also write it in terms of, I should say, the power. You see that it's going to give you square root of the x. Then you take absolute value of the x outside. Okay, because you know that the thing comes outside, it has to be positive. Then as a result, by doing this, you see that you get the absolute value of the x should be 0. And if absolute value of the x is 0, necessarily you understand that here x is 0 itself. Then as a result, by doing these very simple steps, I show that by using some kind of the key things that we needed to remember from the basic algebra, we saw that the x-intercepts as the first clue that we had to find in order to plot this function, x-intercept has to be necessarily 0. Then I know that the function is going to intercept with this x equal to 0. If also, as a final thing I remember, I said that if I put also x equal to 0 as an x-intercept which I had, if I put x equal to 0, then you see that put 0 square root of 0 becomes 0. 0 minus 1 becomes minus 1. Then you have 0 over minus 1. You know 0 divided by any number, it becomes 0. Then you see that you have a pair that x equal to 0, y equal to 0. This is going to be my x-intercepts. Then the origin of the reference frame is one of the points that the function is going to cross. Okay, now we are back to do the actual thing. I'm interested to play a game, and in that game, I'm curious to know how the function which is given, which is expressed in algebraic format, it looks like. You're just going to put the mirror on that to see how it looks like. The mirror that we are just going to use to see how the function looks like is just a Cartesian frame. We are just going to see that if we put the Cartesian frame in front of this function, how it looks like. That's a fun way to see, that's a fun way to explain what is a plotting of the function. The first step which we are going to do, I'm going to say we have 5 steps to take. The first step is that we have to find the intercepts of the function. We'll look at the function first, and we are going to be first curious to answer one question. If I plot this function, in which points it's going to intersect with the horizontal axis, which is the x-axis, and that's what we call that the x-intercepts. Now, in order to find the x-intercepts, remember, the function, if the function is this, is the Cartesian frame is this, which I'm just going to show that. This is the y-axis, this is the x-axis. I have, let's say, a completely random function plotted on there. You see that this function, it plots, if I call this function f of x, you're going to see that this function crosses the x-axis just at this point, and I'm going to call that x0. What is interesting about that x0 is that when you put your eyes along this direction, this is my eyes, this is my eyebrows, this is my eyeball. When I look at the function, the x-axis from this direction, and when I focus at the point x0, which I'm calling that x-intercept, I see the value which I read for the y mapping is going to be 0. And that gives me a clue that in order to find the x-intercepts, I have to find y equal to 0. Then if I put y equal to 0, in order to find the x-intercepts, then as a result I get 0 should equal square root of the x over x squared minus 1. Now, the key thing now, in order to ask for the x-intercepts, is to find the value of the x that is going to validate the expression which I have written there. First of all, I'm going to remind myself on very key things which I remember from the past. I remember from prior studies that if I have a rational expression which is going to be a over b, if a over b becomes 0, I remember I have one key fact. Necessarily in that case, a has to necessarily be 0 in order that the rational expression which I have, a over b, becomes 0. I'm just going to use that identity into solving this expression. Now, I'm just going to erase these coordinates. Then if I do that, I remember here, this square root of the x, it's like the a which I had, then it has to become 0 in order to solve it for the x, that y becomes 0. Then I say that y, square root of the x has to become 0. Now in that case, I'm going to ask myself, in order to do that, how to solve this? In order to solve this, again, I can use one other identity. The other identity which I remember is that if a is equal to b, I can just take both sides raised to the power 2 in order to still preserve the equality between them. I'm going to do the same thing with this. I'm going to take both sides raised to the power 2. Then what do I have here is that I have square root of x, which is going to be raised to the power 2, equals to 0 to the power 2. And you see that in that case, we have another identity, if you are just going to remember, is that if this is this one here, 2 is over there, 2 can go inside, I should say, because like what? Becomes like square root of the x multiplies square root of the x. Then it becomes what? Then in that case, you can also write it in terms of, I should say, the power. You see that it's going to give you square root of the x. Then you take absolute value of the x outside, okay, because you know that the thing comes outside, it has to be positive. Then as a result, by doing this, you see that you get the absolute value of the x should be 0, and if absolute value of the x is 0, necessarily you understand that here x is 0 itself. Then as a result, by doing these very simple steps, I show that by using some kind of the key things that we needed to remember from the basic algebra, we saw that the x-intercept as the first clue that we had to find in order to plot this function, x-intercept has to be necessarily 0. Then I know that the function is going to intercept with this x equal to 0. If also, as a final thing I remember, I said that if I put also x equal to 0 as an x-intercept which I had, if I put x equal to 0, then you see that put 0 square root of 0 becomes 0, 0 minus 1 becomes minus 1, then you have 0 over minus 1. You know 0 divided by any number, it becomes 0. Then you see that you have a pair that x equal to 0, y equal to 0. This is going to be my x-intercepts. Then the origin of the reference frame is one of the points that the function is going to cross. Okay, now, on the previous step, what did I notice? What did I find? The first clue that I got from this function, I noticed that this function, if plotted on the Cartesian reference frame, it is going to cross the x-axis at point 0. I'm going to go to this step number 2, which I'm going to find the y-intercept. As the name implies, imagine that you have this Cartesian frame, which is going to be x and y. In this Cartesian frame, you know that if you have a function and it's going to arbitrarily, for example, I'm just going to cross, if it crosses the y-axis, and I'm just going to staring at that point, from this point, I notice that the y-intercept, it has a very important characteristic. And the important characteristics of that function at the y-intercept is that if I look at that, I see that regardless, it can be anything, I'm just going to call that y0, the x is going to be 0 for that. Then the thing is that whenever you just want to find a clue, you have to go for that, to search for that. What is going to be the x, y-intercept, you have to put the x equal to 0, because that's what it implies. I'm just going to put x equal to 0, which coincidentally, we notice that x equal to 0 is our x-intercepts, and solve the value of the function if the x is for 0 for that. Then what happens then is that I'm going to say y, which I'm going to call that y0, which represents the y-intercepts, should be equal to, I put the square root of the x. I know that the x is going to be 0. Then it becomes square root of 0, 0 to the power 2 minus 1. Now, that's easy to find it. Square root of 0 necessarily has to be 0. Square root of 0 to the power 2 becomes 0. 0 minus 1 becomes minus 1. Then here we have a very important identity that 0 over any number I'm just going to call that a, it becomes necessarily 0. Then as a result, this expression vanishes to become 0. Then what does it tell me? Is that also the y-intercept for me is the point 0, which it becomes like step number 1, which I took. Then the x-intercept is 0 and the y-intercept is 0. By now, I have two important clues about this function. I know that my function is going to cross the x-axis at 0, and I know that it also crosses the y-axis at 0. It means that the origin of the reference frame is a point in that function. Okay, the next question that we have to ask ourselves in order to continue plotting this function is that we have to ask ourselves how the function is going to behave when x and y goes to infinity. What do I mean by that? For example, imagine that you have the y-x coordinates plotted here. You have the y-axis, you have the x-axis. Then the question that you're going to ask yourself is this, that for example, what happens if you stand here on the x-axis and you're just going to go so far along the x-axis? I mean, horizontally you move so far. That's what it means, horizontal asymptote. Symbolically, I show this one like that. We say that what happens, how the function is going to respond back to you if the x, which is going to be the horizontal axis, goes too far. Symbolically, I show that this one. Remember, infinity is not a number, but that's the symbol. Now, in order to find this, you're going to see that also in the calculus class. The method that you're going to do is that you have to divide both the upper term and the lower term by the highest variable in terms of the exponent, which is going to be x squared. If you do that, you're going to see that, for example, the highest that we have over there, I can write it like that, x is to the power 1 over 2, because remember, by the function 11s that you learned, the square root of the x is actually x to the 1 over 2, and x squared, the highest ranking over there is x squared. You're going to see that the rate of the increase, let's say, along, I should say, that direction. For example, if you divide both sides to the x squared, you're going to get something, for example, you see that the denominator is going to grow much faster. Then as a result, when x goes to infinity, for example, you see that if you divide this, it becomes x 1 over x to the power 1 over 3. Then you see that when x goes to infinity, the numerator grows less than the denominator. Or you can say that, for example, if it goes like that, you can divide both sides by x to the power 1 over 2. You see that it becomes 1 at the numerator, and it becomes x to the power what? 3 over 4. Okay, now, then you see that when x goes to infinity, you see that infinity 1 over infinity, this is also approaching to 0. It's like, for example, you have $1, you are dividing that between million people there. You're going to see that the share that each people are going to get is going to be almost 0. And that's the reason that we get these expressions there. Then as a result, for this thing that we see that, the horizontal asymptote is this one. We got that when x goes to infinity, I'm going to write it like that. When x goes to infinity, y equal to 0 becomes the horizontal asymptote. And you ask yourself, what is a y equal to 0? If you go to the Cartesian plane, you see that the x-axis, the equation for that is y equal to 0. Because you remember, any points, any numbers along the x-axis, it has the mapping along the y as 0. That's why y equal to 0 is the pattern of all the points that they are along the x-axis. Then you see that for this plot, y equal to 0, which is the x-axis, plays the role of horizontal asymptote. Now, The next thing that we are going to do, I'm just going to do still the same thing in order to find the vertical asymptote. For the vertical asymptotes, the thing is going to be much easier. Why? Because now we do the same thing. I'm just going to stand on top of the y-axis and I'm just going to go so far. And I'm going to see that in order that it happens, I'm just going to erase this part, which was the horizontal asymptote. And I'm going to see that if y is going to go to infinity, how x is going to behave in order y goes to infinity. Then symbolically, I'm just going to say that y is going to go to infinity as long as you're going to see that. We have a rational expression. I'm just going to write a simple note here. You remember if you had a function g of x, if g of x is a rational function of f of x and h of x. You remember that when h of x goes to 0, the function may behave irrationally and g of x goes to infinity if f of x and g of x both at the same time they do not go to 0. Only the h of x, which is the denominator, goes to 0. Then it means that the denominator which I have over here, x2, x squared minus 1, it gives me a clue. Then x squared minus 1, it should go to 0, becomes 0, in order to have the y goes to 0. Then if you solve this, you're going to see that x should be equal plus or minus 1. Because plus or minus 1 are the roots of this expression. You substitute in there, you see that it becomes 0. Then you see that in order to answer the question of what are the vertical asymptotes, because on the vertical axis we are just going to move all the way up there, so far we see that this equation, that x equal to plus or minus 1 becomes these two lines. For example, x equal plus 1, x equal to minus 1, these two lines becomes the vertical asymptotes. Then now in this part we'll learn that if along the x direction or along the y direction, if we decide to move so far, how the function is going to react. How it's going to react? When it goes to infinity, it's going to get approached to our vertical asymptotes. But the key point is that it's not going to cross it. And also, as y equal to 0 is a horizontal asymptote, as you move far along the x-axis, it's going to just stretch along the x-axis, but the key point is that it's not going to cross and touch either horizontal asymptotes or vertical asymptotes, but it's going to get close as possible as it can. Okay, now, we answered 4 questions so far. Now we are just going to the 5th most important questions before we just get to know how the function may look like if you place it on the Cartesian plane with respect to the x and y axis, which we call this plotting the function. Now, so far we understood about the intercepts, we talked about the asymptotic behavior of the function, and the last thing that we need to know is that what is the plate of the function? By the plate of the function, I mean what is going to be the inputs into the function itself. That's essentially what we call that as a domain of the function. In order to find the domain of the function, I'm just going to call that D. You remember from prior studies that we had, we saw that if we can design a function, we designed a function f of x, which is going to be a rational function because it comes with the numerator, which is a function itself, and it also comes with the denominator h of x, which is a function itself. You remember on the previous studies that you had, we said that for this type of functions, in order to find the domain, becomes the set of all the x-axis becomes x, that x is a real number. However, for that x, h of x should not become 0. That was a thing that we have discussed about that in your courses before when we talk about the domain of the function. Why? Because we say that we are restricted in a sense that have our denominators approaches to 0 if you are working with a rational number. If you're working with the square roots function, you know that you are restricted to have all the things inside, underneath the square root to be positive. Then as a result, Now when I look back to the function which I have over there, and I see the denominator is x squared minus 1, I know that x squared minus 1 should not become 0. And when we're talking about the vertical asymptotes, you saw that by x equal plus or minus 1, the denominator is moving towards 0. Then that's the thing that we are restricted. We cannot do that. Then as a result, I'm just going to come here and say that the domain of the function, then they are going to be all the real numbers, however, the x should not be equal to plus or minus 1. Okay? Then if that's the case, I know that the vertical asymptotes, which I have plus or minus 1, which I have it there. Okay, then I know that it is not necessarily, that this is not going to be also the same thing that we discussed on the vertical asymptotes. Now, but at the same time, we have another criteria that we have to look into that. But also remember from your prior studies, I'm just going to show that here as a point 2. I'm just going to call this point A. I'm just going to call that point B, that when we're talking about the domain, we said that if we design a function, we call that f of x. We design a function, we call that f of x. And this is the square root of another function, we call that g of x. G of x can be any form, like the square root of the x. When we look at this one, we said that the domain of this function is all the real numbers, however, x has to be positive. Because under the square root, you cannot have a negative number, then you're restricting yourself to the positive numbers. Here we have those two cases at the same time. We have a rational function, which is point A. We have the denominator, which we avoided to approach it close to 0. And also we have a square root that we are going to be careful based on point B that it should not become negative underneath. Then as a result, we are just going to modify our domain that our x also has to be necessarily a positive number. You are combining these two things together. You said that x has to be a positive number, and at the same time, x cannot be plus or negative 1, which it means that negative 1 cannot be also a vertical asymptote because negative 1 is not part of the domain. You're going to see that when we plot the function. Then this is going to be how we defined the domain of that function. Okay, now we saw that what is the domain of the function. Now we are just going to see that if we see that in our plates, which is a function, these are the inputs that we can take, how is going to be the output? And by the output, I mean the extent of the output that we can get from the plates of the recipe that we have for the function as an input. In order to answer that question, we are just coming back to talk about the range of the function. For the range of the function, we are going to be a little bit cautious because we are just going to see the extent of the range. We know that the numerator is always a positive number because we know that based on the range based on the domain that we explained over there, and the x has to be positive number and not including plus or minus 1. We are just coming to see that also. We're going to see that here, if the numerator is going to be a positive number, the denominator, in terms of to see how it changes, we can decide it in that way. Whatever is going to be this one, the sign of the denominator is going to make a big difference because this is a positive, and that's how we are just going to work on it then. I'm just going to say, okay, in order to see the extent of the range, I'm just going to show you the x-axis over here. This is going to be the x-axis, and the origin lies somewhere over there. Along the x-axis that I have here, in this particular question, 2 points are so conspicuous, which is plus and minus 1, which will identify that. Y equal to 0 is something different. I'm looking at the x-axis. I'm just going to highlight this one. I know that this is minus 1. This is going to be plus 1. Arbitrarily, I'm just going to choose that. I'm just going to take this one over here. Okay, I'm just going to take this one over here. And also, at the same time, I know that x equal to 0, which is going to be the root of the one which we have over there, is this. I'm just going to do that one. Okay, first, I'm just going to look how the function behaves in these two parts. First of all, for this one, I'm just going to show that the square root of the x. Let me take this one a little bit further. I'm just going to say that the square root of the x, it's going to be x squared minus 1, and this is going to be the function itself. Okay? Now, that's what we are going to do. The first thing that I'm just going to do is this one. I notice that I'm looking at the numerator, which is the square root of the x. I know that for this one, 0 is the number that we had over there. For this one, I know that if I'm looking at the 0, the function becomes 0 over there. There is nothing at the other side because I know that everything is going to be positive. Everything is going to be positive. This one is positive. This one is positive. This one here, I know that for the square root, for the negative numbers, nothing exists. Now, I come to the denominator. I know that if it becomes plus 1 and negative 1, it becomes 0. I have my zeros over there. Okay? And for negative 1, it doesn't exist at all. Now, I know that if it becomes, I'm just going to choose what happens. Okay, between minus 1 and plus 1, what happens? For example, I'm just going to choose something, let's say, if you choose something bigger than 1, I'm just going to choose randomly a number to assess the sign. If I choose plus 2, for example, plus 2 is something bigger than 1. If it's going to be bigger than 1 plus 2, it becomes 4 minus 1 becomes 3. Then I know that if number is going to be bigger than 1 on the x-axis, just for the function x squared minus 1, it gives me a plus sign. At plus 1, it becomes 0. Then focus, I'm looking into on the middle row over here. Something between 0 and 1. Okay, now let's go to this one. Let's decide these ones. For example, I'm just going to choose minus 2 over there. With minus 2 also, I get something positive. Because minus 2 to the power 2 becomes 4. 4 minus 1 becomes 3. Then either less than minus 1 or plus 1, it becomes positive. Now, if I put the 0 there, what happens? If I just go with something in between, for example, I'm just going to erase this. Between this one, if I just go for something between plus 1 and minus 1, if I put something between them, for example, 0 is the easiest one. If I put 0, it becomes whole negative. Because 0 minus 1 becomes minus. You put 1 over 2, which is between this one. 1 over 2 becomes 1 over 4 minus 1 becomes also a negative number. Then by doing this, I decided how the function is going to have the number. But look at that. I'm looking at the range overall. Then it means that I have to divide these sides together to get the overall spectrum of the function. I know that if this becomes 0, this one, I know that the function at this point, it becomes infinity. It does not define because it becomes the asymptote. Plus over plus, it gives me a positive sign. Plus over negative, it gives me a negative sign. Okay? And I'm just going to stop here because remember, for the domain which I have, when it comes to the whole function, now I'm looking at the third row. This function comes only with this domain. Then the only thing which I'm just going to care about is that I'm looking at the x's, which they are positive, greater than 0, and they are not plus or minus 1. Minus 1 is going to be excluded because it's only negative, and also plus 1, it's going to be excluded because look at this one. Because if you have a plus 1, it becomes a negative, an infinity number. Then as a result, the range of the function that we have, it is, and this side, we have no definition of that because this one is not part of the function because this one is not defined. The negative numbers are not defined. Then you see that for the range of the function, which we can think of it right now, we know that the range of the function y can belong to all the real numbers, however, less than 1, we say that y for x less than 1 and bigger than 0, y is going to be negative. Otherwise, for x greater than 1, we have y is going to be what? Positive. This has become the range of the function that we have decided. Now, the next thing that we are just going to do, now we have 5 information, which is going to be the domain and the range also included there. Then now we are ready to just move on to see how the function, by incorporating all these things, may look like then. Okay, now, at this stage, we have come to decide how this function may look like if we put this on the reference frame, on the Cartesian plane, which I plotted here. First of all, remember, we have to start with the Cartesian plane, which are two normal axes, x and y. I have gone through so far, and I have shown the vertical and horizontal asymptotes there. You remember the horizontal asymptotes? On point number 3, we decided it has to be y equal to 0, which is essentially the x-axis. We decided the vertical asymptotes has to be x equal plus or minus 1, parallel lines with respect to the y-axis, but crossing plus 1 and minus 1 on the x. But because on point number 5, we decided that the domain of the function has to be a positive number, then we cannot include x equal minus 1 as a vertical asymptote yet. Take a note here. And also, we notice that the points that we had over there, which is x0 and y0 as an intercepts, we notice that the point 0, 0, it becomes, the origin is both the x-intercepts and the y-intercepts for our function. Now, we have shown point 1, 2, 3 and 4. We know by the 5, we know that we have to start just the x positive number. Now we are more focusing on plotting the function on points 5 and 6. Point 5 says that if you are just going to start to run, imagine yourself standing on the x-axis, you are planting the seeds of the function. You know that you should not start on the left side of the 0. You have to stand at the positive number, because the positive number is the one that the domain of the function shows. Then you have to stop over there, start running towards the right, because you are exclusively said that x has to be positive, but at the same time x has not to be plus 1. It means that anywhere you draw your map, you should not cross this line. And that's why you call it vertical asymptotes. Vertical asymptotes, as we discussed, it means that the point, the lines that the function gets asymptotically close, infinitesimally close, but they do not cross it. But at the same time, when we now look at the range to see that how you are just moving your pen along the y-axis, we say that if you are between x 0 and 1, the function is going to be negative. You are plotting there. Then it means that the x between 0 and 1, you are harnessing the y, which is going to be negative. Then imagine you are walking between 0 and 1. You do not look up there. You look down there. But you have to get close to the vertical asymptotes, which is there. You are just going to start from the intercepts, then move all the way down there. But at the same time, you are going to see that we said that when the x becomes bigger than 1, when we decided on the range definition, x is bigger than 1 means that you are standing over there, the y becomes positive. But how it becomes positive? Do you look? Now, also, for the other one, you saw that, okay, when the y becomes positive, when the x is bigger than 1. But the problem is that with this one, we have one vertical asymptote and one horizontal asymptote. For this one, I have to change a little bit line because, look at that, we have to also be close so much to the horizontal line and go to the vertical line. And also when the plus one we are looking at, we said that we are confined between these asymptotes. It means that we have to be the positive number, but we have to be so close to the vertical asymptotes, then going to the horizontal asymptotes. And remember, the key point in plotting the function is that you never ever are going to cross either the vertical asymptotes or horizontal asymptotes, because these are the lines that you are just going to get as close as possible to them, but you do not touch them. then you're going to expand over the vertical and horizontal asymptotes that we have shown it here. Now, I hope these methods that we used, these 6 steps and these 6 clues that we were able to get, you saw that how made it much easier to identify how the function may look like then.